repeat it, and we'll hear something that we've heard and understand it. So we're very, very pleased today to have Robert Guralnick of USC and visiting Princeton speak to us on strongly dense and free subgroups.
Thanks, guys. Thank Dennis for the invitation, and also I'm at the Institute and partially at the university for the year, and I'm on sabbatical, but I'm also being supported by a Simons Foundation Fellowship, so it's appropriate that I'm here as well. So I have a lunch over there, but it's too much. It's a big lunch, yeah. Because the Institute also has nice lunches. So I wanted to talk about strongly dense free subgroups, or some permutation of those things. So before I forget, most of what I'm going to talk about is joint work with Emmanuel Breuillard. And Ben Green and Tara Tao. And if I get a chance, there's some more recent work on this with Breuillard and Michael Larson. Okay, so before I tell you what a strongly dense free subgroup is, hopefully I know what a free subgroup is, but
can you shout a little bit? I'm having a little trouble hearing.
Sure.
Oh yeah.
So I think Hausdorff was maybe the first person in 1914, I think, proved that there were free subgroups in SL2. I think he did know this with us. But, and he just wrote down two generators, two rotations, or two generators, or if you want to do it in SO3, either way. And just proved that that no word, there's some vector that no word fixed, and so we have free subgroup.
So in SO3.
In SO3,
Okay.
or SL2.
What did you write?
Well, SL2 is the same as SL3. It's essential modulo. PSL2 was SL3. Right.
Wait, you mean the Lie algebra is the same?
The Lie algebra is certainly the same, and the groups are essential. They're isogynous. Anyway, doesn't. Okay.
I've already lost. SL2R is a non-compact Lie group, isn't it?
No, well, right.
SL2
So
is a compact Lie group.
let me just see how's that. And then PSL2 is SL3.
Oh.
So I'm an algebraist, so I'm thinking characteristic P. So.
Okay.
Although I will mostly talk about characteristic 0 and then say what you have to do to make things work in characteristic B. Okay, we'll see in fact that there's lots of free subgroups floating around. In fact, most of the time you're going to hit one if you try. In fact, then Tits proved something which is now called the Tits alternative. You can call it this, which says suppose that T is a finitely generated subgroup of a simple, say, new group. Or actually, let me just say simple algebraic group. So think of SLI. And then either G has a finite index subgroup that's solvable, or G contains free subgroups. you could just, I mean, since any algebraic group is contained in GLN or SLN, so you could just think of it as that statement. So you have a linear group. It's either virtually solvable, I mean, up to a finite index subgroup, or it contains free subgroups. So you have this really dichotomy. Either you're essentially solvable, or you're as far from being solvable as possible. There's no, you have subgroups with no relations. Okay, and moreover, you could prove a bit more. Moreover, if G is Zariski dense, in this simple algebraic group, let me call it S, then there exists Zariski dense free subgroups.
What?
There exists, if G is Zariski dense in the simple group S, simple algebraic group, then there exist free subgroups that are also Zariski dense.
That's almost immediate, right? Because the algebraic closure of a solvable group would be solvable.
No, right, but you can have, I mean, so for example, the algebraic group could be SLN, and you could have a free subgroup of SL2 inside the SLN. So it need not be Zariski dense.
So the free group I'm happy with, and solvable and vaguely remember, but Zariski dense I need to remind me.
Okay, so if you want to think of characteristic zero, think of the usual topology and that stuff. So the Zariski topology is sort of a substitute that works in positive characteristic as well. So the closed sets, you have a variety, and that's an affine variety, and the closed sets are the zeros of some collection of polygons. So that's the topology.
Closed subvarieties.
Right. Right. Those are the closed subvarieties, and so to say Zariski dense, it just means that it's dense in the Zariski topology. So the closure is everything.
So this second case, you're assuming that G.
Well, if G is Zariski dense in S, it's certainly not virtually solvable. Because then the closure would also be virtually solvable. So that is correct.
Oh, but we didn't hear his question.
I did hear his question.
I didn't hear it.
Okay. His question was, I didn't have the alternative, the two cases. Then it could have been virtually solvable. But the point is that it's Zariski dense in a simple group, simple algebraic group, it can't be virtually solvable. Because then the Zariski closure would also be virtually solvable. I mean, simple Lie groups or simple algebraic groups are not virtually solvable since they're simple. All right. So I want to sort of put these properties together in a slightly to show that really this is a very frequent occurrence, number one, and some applications of this idea. To various kinds of issues. One being an old paper of Deligne and Sullivan that I'll talk about. But the motivation, so I got involved with this project with Breuillard, Green, and Tao. There was a meeting at the Institute a few years ago, and Emmanuel came up to me and asked me a certain question related to this kind of thing. And I said, oh yeah, I think I can do this. So that's how it started. And it was because of some question about expanders, graphs, certain graphs being expanders, which I'll talk about a little bit later. But we don't. The idea is just quite nuts anyway. So let me tell you. So let me give you a definition of strongly dense. So let's suppose that S is a simple algebraic group. Again, if you're more comfortable, just think of a Lie group, think of SLN C, that's fine. Then we say, G, which is a subgroup of S, is called strongly dense. In S, if every non-abelian subgroup of G is Zariski dense. So not only is G Zariski dense, but take any, of course, abelian subgroups are going to have a hard time being Zariski dense in a subgroup, so you really can't expect that. But anything else, any non-abelian things, and particularly we're going to really stick to G free. So we'll typically assume want G to be free as well. Get G to be free. So we want to produce free subgroups with that, which have this property. So, and of course, in a free group, every subgroup is free, and it's not abelian unless it's cyclic. So what we're saying is for G is free, it says every non-cyclic subgroup is Zariski dense. Well, if you think about Hausdorff with SL2, a free subgroup is Zariski dense because the only subgroups of SL2 are either are solvable, or virtually solvable. They're either finite or in any case, the connected component is solvable. It's proper. It's either a torus or a Burrell subgroup. And it's pretty clearly those don't contain free subgroups. So any free subgroup is Zariski. There aren't any other closed subgroups, so any free subgroup is Zariski dense. And any non-abelian subgroup of a free group is still a free group, so it's also Zariski dense. So in SL2, you have this property automatically. Okay, so we want to prove that such things exist, and not only exist, they're ubiquitous. And the idea is not all that difficult. So let me start with, here's a fact, easy fact, which I think lots of people probably knew. I'm not sure who first wrote it down. Certainly in special cases, variations of it. Let's let G be a simple Lie group or a simple algebraic group of characteristic 0. It's not quite true in characteristic B, and I'll say what the difference is. But think of a Lie group, that's fine as well. Then if I look at the set of pairs in G cross G, let's stick with S, in S cross S, such that the subgroup generated by A and B, the Zariski closure of this, so the closed subgroup generated by this, is S, is an open subrow. Meaning almost all pairs have this property, in whatever sense you mean open. So the point is in Zariski topology, especially open sets are huge. So for example, if you have the affine line, the open sets are, well, aside from the empty set, are cofinite, so that you're missing only one thing. Okay, so this is actually pretty easy to prove, although it's not quite as obvious as you think. I mean, so what's the idea of this proof? So the point is, take a representation, a finite dimensional rational representation of S, and what's the condition that that a pair generates an irreducible subgroup, it's acting irreducibly? Well, that's just saying that the algebra generated by those elements in the representation is the full matrix algebra over the field, which is just saying that the span of all words in those elements has dimension n squared. And failing to have that says that the rank, the linear span of any finite subset of those things has dimension at most n squared minus 1. In fact, quite a bit less typically. But in any case, and that's a closed condition. That's saying that all write things in terms of a basis. It's saying that all the rank of a certain matrix is less than n squared, which is saying all the minors, n squared minus 1 by n squared minus minors are 0, which is, of course, a closed condition. So failing to generate an irreducible subgroup in a given representation is a closed condition. So now let's take the adjoint representation. Let it act on all the algebra.
Wait, but these are equations and the targets and the matrices.
Yes. Right.
And
It's a representation, which is a
so the
continuous map.
representation might go into that subvariant.
Not so. We have this representation rho into GLN A bar, whatever the field is, and so I'm just looking at. So I'm taking. So I have A and B, so I'm just looking at all words. Rho of A to that E1, B to the E2, etc. And taking this linear span of these guys. And I'm saying the condition that it's not irreducible is that it is a closed condition. It's polynomial equations on these things. This is continuous in the Zariski topology, so that puts that's a
It's a condition that what? It's not.
the condition that these guys do not generate do not act irreducibly in this representation is equivalent to saying they don't generate the full matrix algebra, which is a closed condition. It's the same as the span of these guys is too small, and that's a closed condition.
It's a closed condition for pairs of elements in GLN, right?
Yes, and I'm just restricting the image of S cross S, so rho of S plus rho of S, which is a condition on S.
Well, you're supposing that this isn't a reducible representation.
Yeah, this is irreducible.
So it's
So for
not
any
contained in that closed subset.
That's right. And so I'm taking any particular irreducible representation that has this property. So in particular, let's apply it to the acting on the Lie algebra. And so notice that if these guys do not generate, if the Zariski closure is not S, it's generating some proper subgroup, closed subgroup. I'm taking the Zariski closure. And so then the Lie algebra of that would be invariant in the adjoint representation. And so it would not be. So just applying this criterion to the adjoint representation, it says the set of pairs where whose Lie algebra of the group generated by them is a non-trivial Lie subalgebra. That's open. And you think, oh well, I'm done. Well, not quite, because there's two possibilities. If it's positive dimensional, then the Lie algebra is certainly not trivial, but it could be a finite group. And in fact, there are finite groups. There are examples where there's a finite subgroup of your algebraic group, which does, in fact, happen to act irreducibly on the Lie algebra. Not so common, but it certainly exists. Like, for example, inside SL2, we have SL2-5, and that acts irreducibly on the three-dimensional Lie algebra of SL2. So you can't necessarily just use the adjoint representation, but you use some other one. The point is, for finite subgroups, you can certainly find for any given finite subgroup, or in fact for any finite subgroup, you can actually find a representation where no finite subgroup can act irreducibly. For example, in characteristic 0, you can just use Jordan's theorem. If you have a subgroup of a finite subgroup of GLN, then Jordan's theorem tells you that there's an abelian subgroup of bounded index, depending only on n. And that tells you that there's a bound on the dimension of irreducible representations. And so you just, on the other hand, any simple Lie group has arbitrarily large irreducible representations. And so you can avoid this. So you might need to use a second one. You can always get by with one if you really wanted to, but certainly 2 is suffice. So this is an open subarray. I didn't tell you that it's not empty yet, though. So then you also have to show it's not empty. And in characteristic 0, that's fairly easy. What you do is, let me do it, say, for SLN. So you can choose an element in SLN, and let me look over the complexes, even though you can do this even over Q1, it doesn't matter. You choose a generic, you take a diagonal matrix with distinct eigenvalues, in fact, generic. So, for example, the eigenvalues being algebraically independent, subject to the relation plus the product is 1. So the Zariski closure of that single element is the full torus. There's no algebraic condition that will satisfy, so it won't be a proper subtorus. And now if you have a maximal torus, there are only finitely many closed subgroups containing a maximal torus, because think of it in terms of the Lie algebra. The torus is acting on the Lie algebra, and what are the eigenspaces? There's the torus, which is the zero eigenspace. And there are the root subgroups, which are one-dimensional distinct eigenspaces. And so there's only finitely many Lie subalgebras that are invariant, which contain the full torus. And so there's only finitely many, so you take the union of those things. That's a finite union of closed subsets. It can't be the whole thing for proper ones, because it's an irreducible variety. So there has to be something, in fact, lots of things outside the union. And so it's not empty. So this is not. So most pairs generate a Zariski S. And then we can combine this with the fact that Hausdorff proved that there are free subgroups. We know that there's free subgroups. We can also look at the subvariety. I'm going to look at the set of pairs.
I have a stupid objection, but this S has to be positive dimensional.
S is positive. I mean, simple algebraic groups have dimension at least 3.
What about zero? What about finite simple groups? They're algebraic groups. I just said it's equivalent.
When I say connected, okay? Sure. Connected.
Being like offer,
No,
yeah.
that's okay. No, you're right, it's connected. They're connected, or positive dimension. So now let's let F sub 2 be a free group on 2 generators. And let me take a non-trivial element in the free group. And now I can look at the set of pairs such that again, an S cross S, where that word doesn't vanish. Okay. Dip the hand there. So this is an open subgroup. And again, not empty. I mean, this is clearly equal 1 is a polynomial equation. So, and it's not empty because there are free subgroups. So inside there, so that I can find A and B by Hausdorff, for example, because there's always an SL2 inside my algebraic group, so there's certainly a free subgroup somewhere. So this is a non-empty open subgroup, and therefore I can do both things at once because the intersection of a non-empty open subvarieties is open. So in fact, the things that the pairs A and B, where W of A and B is non-trivial, and they generate a Zariski dense subgroup, that's also open. So there's lots of things. And now, let's just point out, because this is in some sense the idea behind what I've improved the strong result, which is a bit more complicated, but it's the same idea. So if I look now let S be, say, a simple algebraic group over C. And the complex number. I don't really care that it's complex numbers, I just want it to be uncountable. And then I want to, again, F2 is a free group on 2 generators. And I'm going to take all pairs A and B such that this Zariski closure is S, and that W of AB is not 1 for all non-trivial values. Okay, well the point is this is if I look at the ones that don't generate S and the ones where this is 1 for one of these things, that's a countable union. So this is the complement to a countable union of proper subgroups. if you want to think of it from an analytic point of view, proper subgroup have measure 0. I'm taking a cannibal union of them, so that still has measure 0. So the point is, this is still a tiny set. And so what it tells you is that, in fact, almost every pair has the property that the Zariski closure is everything, and W of AB is not 1, meaning it's a free, they generate a free subgroup. So this says that the set of pairs that are Zariski dense and generate a free subgroup is generic in whatever sense, in the sense that it's missing just a measure 0 set, or it's a complement to a
I couldn't see and hear the argument over there. So how did you prove that WAB in a simple group, the set of elements pairs to satisfy a relation? What's the proper?
Well, it's certainly, it's the ones that are equal to 1, that's a polynomial condition.
Right.
So it's closed.
Might be everything.
Might be everything except by Hausdorff, for example. We know there's always a free subgroup.
Oh, right.
So there's some pair.
Okay.
So the point is, as soon as you have one free subgroup in there, it tells you almost everything is in that sense. Okay. Now, in fact, you don't really need to work over an uncountable field because, of course, if you just want 1, because it's a finitely generated subgroup, and we're 2 pairs generated, and they're going to all live in some finitely generated field. So you can certainly do it over
Over the algebraic closure of the...
over the algebraic closure of some field of finite transcendence degree. And you could even, just by sort of general nonsense, you could bound the transcendence degree in terms of the dimension of the group. But in fact, you can do better than that. So now we want to do, so the same thing works in characteristic P. So let me just say that. This theorem still works as long as this field is uncountable in characteristic P, except it's not quite true that the set of pairs whose Zariski closure is everything. That's no longer an open subwriting in positive characteristic. The problem is, work over the algebraic closure of FP, for example. Any pair generates a finite subgroup, so you're going to have a hard time being Zariski dense. And in fact, but even if you have a bigger transcendence degree, the pairs that generate a finite subgroup is dense. It's not open, but it's dense. And so you can't. So the ones that do generate a Zariski dense subgroup can't be open. It's still quite big, and in fact, it still misses. It's just a complement to a countable union of countable subgroups. Namely, you just have to avoid the things that generate a finite subgroup of order n plus 1, etc. So that's just a countable set. So this theorem is actually true in characteristic P for an uncountable.
On the characteristic, closed subgroups have measure 0 with a Haar measure?
They're not compact, so there is no Haar measure in characteristic. For algebraic groups.
They're not locally compact.
Well, the Zariski topology is a funny topology. It's compact.
Not for that topology, no.
Well, what topology do you put in characteristic?
P-adic topology.
This is not, I'm not always p-adics, I'm in characteristic P. So there is no Haar measure. Okay. So we want to do the same thing.
Why is it big then? It's a complement of a countable union.
Yeah, it's a complement. Yeah, so proper subvarieties are still small. There's the notion of the dimension of a subvariety, so they're proper dimension. And you have a countable union. At least if you're over on a countable field, countable unions of things are small. So, for example,
Small in what sense?
well, you're still in the sense that it's not everything. For example, I mean that's one sense. But so, for example, a vector space over an uncountable field is not the union of proper subspaces. And you have the same notion for subvarieties.
So you have this notion of category in the context sometimes.
Yeah. Okay.
The whole thing is not the countable union of
Yeah. So over countable,
of small things,
right.
of closed number dense things.
Of course, if you're over
Wait,
countable.
wait. So the whole space is not the countable union of closed Zariski closed sets.
Right.
Okay.
Of course, if you're over countable fields, then you can't hope to do that because it's a countable union of the points, and the points are closed. So, but as I said, you can come down to finitely generated fields by just because the group subgroup.
How do we get what's the easiest way to get an uncountable field? In this
Just
context.
take FP and join uncountably many indeterminates.
Not very easy.
That's, okay. I guess maybe you can work with power series and do it a little bit better if you're slightly more detailed.
Power series, yeah.
Okay, so now the theorem.
Then you would have hard measures for power series.
I don't think so. Not
Yes,
positive.
topology now.
It's
topology.
Well, okay. So if K is algebraically closed, positive characteristic or not, and it's uncountable, then and S is a simple algebraic group. Over K. Connected implies that the set of pairs in S cross S such that the group generated by A and B is free and strongly dense is generic. In the sense that I meant before. It's the complement to a countable union of proper subvarieties. And the idea of the proof is, okay, so now not only do we have to say that
the definition of strongly dense again because it changes when you have a free group. So
it just means that every nonabelian subgroup is Zariski
That means
dense.
every non-cyclic subgroup.
Every non-cyclic subgroup.
Every non-cyclic subgroup of that is strongly dense.
Right.
Okay.
So what we need to show, really, if you think about it and use the same proof, what we need to show is the following. If W1 and W2 are two elements in my free group, and they don't commute, W1, W2 is not W2, W1. So then the group generated by W1 and W2 is a free non-abelian subgroup. And then we want to prove is that the set of pairs A and B, such that the group generated by W1 AB and W2 AB, that's Zariski dense. If you think about it, this is what we need to prove, because then there's only countably many pairs of words. So for each one of these pairs, this is an open subvariety. The ones that do have this property is open, the ones that don't is closed. And so again, I only have to avoid a countable union of proper subvarieties over an algebraically closed field. So this is all I need to do. Okay.
Well, you just keep the sentence,
So if we
need to show that
we need to show this.
That the set of pairs such that that's true is what?
So the set of pairs, this is, is open.
Okay.
It's open, not empty. Which is the more important thing.
You don't keep saying it, but all open sets are dense. They're not empty, right?
Right. Yes.
You're not saying
In an irreducible subvariety,
right.
Open subsets, non-empty open subsets are dense. That's critical.
Right.
Yes. Thank you. Okay. It's open by exactly the same argument that I gave that for a pair, at least in characteristic 0.
Like Hausdorff.
No, not by Hausdorff. The fact is just whether these guys take an irreducible representation, or the two irreducible representations that I mentioned before that you have to check that these guys are irreducible in those two representations, and which again is an open condition. Okay. So So we just have to check this. And so to do that, we use the result of Burrell, which I'll mention, and Burrell proved this result to sort of extend the results from that were related to what Dennis and Deligne proved, which are the Banach-Tarski paradox for decompositions of spheres. I'll mention that later. So there's a theorem of Burrell. Prove the following. He said, let's let W, I'll just take it to be in two generators. There's then I take a non-trivial element of the free group of two generators. So then let's take S to be a simple algebraic group. And let's take, so if you think about it, then W defines a map from S cross S to S just by plugging in elements.
Called W.
Which is
W,
especially from text and and what Breuillard proved is that W is dominant, meaning that the image contains an open, non-empty open subset of S. And the proof is actually not very hard. In fact, the hardest case, so for SL2, it's Hausdorff-Banach. The existence of a free subgroup is enough.
So I didn't get what is the statement. So for any word W, or
for any non-trivial word W, this map is dominant.
okay.
So the image is big. So most things are W of AB for some parity. For example,
You can solve lots of equations.
right. You can, most of the time you can't solve the equation. And so, for example, this is pretty easy for most cases. Like for E8, the way you prove it is, E8 contains the subgroup SL9. And by induction, the theorem would be true for SL9. And that meaning that the image contains all the diagonal matrices, or most of the diagonal matrices in SL9, but that is a maximal torus of E8 as well. So it means it hits almost everything in E8. Because this image is closed under conjugation. Because it's a word map. So, okay. So E8 is easy. There's nothing to do. So in fact, the only case that's hard to do is SLN. That's the only case that you can't do by sort of induction. SL2 is done. In fact, once you do SL3, you can do all the other SLNs by induction.
But it's full of conjugation, the end things. The end conjugators. Not that far.
So if you take something that's in the image of W and you conjugate it, it's still in the image of W.
Yeah.
So the image of W is closed under
I see
conjugation.
that way. Okay, like that. I read it the wrong way.
Okay. So you just have to hit most of a maximal torus. That's all you need to do. And so if you have smaller subgroups that contain maximal tori, semi-simple groups, then you're in good shape. So how do you do SL3 or SLN in general? What you do is you say, well, by induction I can hit almost everything in SLN minus 1. That means I can hit almost anything that has one eigenvalue 1 and anything else. Now that's a codimension 1 subvariety in some sense. So you have to get things that don't have eigenvalue 1. How do you do those? Well, what you do is you take a division algebra of degree n. Over
So what are you proving now, sorry?
I'm saying how Burrell proved this result. So let's SL3. There's division algebra of dimension 9 over 2, for example, or over the favorite field. One is not a finite field. Over some purely transcendental subgroup.
This is too fast. Take what now?
So you take a division algebra. Let's do it in characters to 0. So take D over Q division algebra. dimension 9, degree 3. So you can, so D sits inside 3 by 3 matrices over C. It sits inside there. Oh, and 3 by 3 matrices, yeah. Okay, because when you tensor up with C, it just becomes matrix, right? It just,
Give a quick reminder of what the structure of division algebras are that you're using right now.
So division algebra just means it's not commutative, but there are no zero divisors.
Right.
Every element
Associative.
and every associative, and every element has an inverse.
Right. And then what's you said take one. How do you know there is one?
So that's the theorem. They exist. I mean, so there's lots of constructions of them. So for example, over Q, there's a nice description of all the division algebras can be described by their p-adic completions. What happens p-adically? You can give a system of local invariant.
Well, I'm not remembering some simple statement due to some famous old algebraist that every division algebra is blah, blah, blah.
Well,
Matrix.
well, it's certainly, so the point is D tensor,
If you did it over C, there wouldn't be very many. Right?
there aren't any, right?
Huh?
That's the whole point. In fact, D tensor
Overall is
C
a little bit, but
is isomorphic to just matrix, right?
oh, the tensor of C.
Yeah, so it certainly sits inside there. Over an algebraically closed field, there aren't any division algebras. They all just become matrices.
Oh, okay, that's right.
So now, and also D star, if I just take,
The units.
really if I want to take SL, so the norm 1 guys, don't let me, I'm not saying much about it, but this is Zariski dense. And SL3. Basically because of this fact, for example, unless you can prove that much trouble. Okay, and therefore, since the word map is dominant, the word map restricted to this guy is also the image will be dense. But of course, in a division algebra, nothing has eigenvalue 1 because everything, there are no zero divisors. So when I subtract the identity, if I have a non-trivial element, a non-identity element, when I subtract the identity, it's still invertible. So it can't have 0 as an eigenvalue. So the original element couldn't have 1 as an eigenvalue. And so the image of this is still big, but it contains elements with no eigenvalues 1. On the other hand, I hit almost everything with eigenvalue 1. That's codimension 1 up to conjugacy. And my image is irreducible because these guys are irreducible, and so as soon as I miss this codimension 1 subgrade, I have to hit almost everything.
Wait, so there's, okay, one's not an eigenvalue, then what did you say next?
So therefore, and moreover, W doesn't vanish on this subgroup because this is a Zariski dense, and so if W vanished on this, it would be trivial on the closure, which is everything, and it's not. And so therefore, but the image of any word map in here, it's not trivial.
Wait, am I supposed to think of this in the domain or the range of this? I'm sort of, where are we working here?
So the point is, this D star, it's not quite true, but almost D star sits inside of this. I mean, this is not quite true. You have to take the norm 1 elements of D star, but that's. And so I can restrict my map W from D star across D star into D star. And the point is, it's not trivial because this is Zariski dense. And therefore, it hits something that's not 1, which means it hits something that doesn't have any eigenvalue 1. But on the other hand, because of applying it to SL2, we know that it hits anything that doesn't. It hits most things that have eigenvalue 1. So putting the two together forces it to be dominant. So that was Burrell's.
I didn't quite get it.
Okay, I think we can talk about it later. You know, anyway, you should have read Burrell's paper since it was followed. So it's the arguments. Okay, so.
Well, I appreciate this point that the division algebra, when you think of elements as matrices, they don't have 1 as an eigenvalue.
Right.
That's a crucial point.
That's right. So the idea.
But then,
So the point is the image of W.
it's
So
easy to finish it from that.
So okay, so So the point is, we know that if I take the image of W, closure, if I take this contains all elements with eigenvalue 1.
At least one eigenvalue 1. Why is that?
Because by applying the result to SLN minus 1. Or SL2 in this case. Because if you apply your word map from SL2 plus SL2, that hits almost everything in SL2, and SL2 sitting inside SL3 contains.
And because you're including it in one more dimension, you get to 1.
Yes, right, exactly. And on the other hand, the image of W contains.
Well, it contains certain elements which have eigenvalue 1.
No, it contains most. The closure contains everything. Because the image of W, the closure contains SL2.
Oh, that's the algebraic closure. So the algebraic closure of the right-hand side is of any set with ones.
Right.
Then one. Okay, fine. All right.
And it contains elements which are not, with no eigenvalue 1.
Right. So it's got this division element.
But this is a hypersurface, and the image is irreducible, and so it properly contains a hypersurface.
And some more.
And the image is irreducible, so it has to be over.
Okay.
That's it.
You have both 1 and not 1.
Right.
That's the argument. Okay.
Okay. So now what we do is the following. We look at now, I'm not going to give the details here, but the idea is we look at the set of pairs now in S cross S. So we're given our W1 and W2 that don't commute. So we look at the set of pairs such that W1 of AB, W2 AB, and the commutator. So these are all maximal Breuillard. So again, think of it, if you're in SLN, I'm saying that this guy has sort of eigenvalues that have no algebraic relation other than the product of the eigenvalues is 1. And so the Zariski closure of the subgroup generated by this is a maximal torus.
Contains.
Well, it is. It's abelian, so it's contained in a maximal torus. So it's actually.
Oh, you took the commutator. Where did you take the commutator?
Well, I took 3 different words. I took W1, W2, and the commutator of W1 and W2, which is not 1 because W1 and W2 didn't commute. So this is a non-trivial word, and so when I plug in AB, I can just apply that Burrell's theorem to that commutator word.
Where's this abelian group on the board? There's no abelian group here.
I'm taking pairs of words W1 and W2 that don't commute. That's where I'm getting my nonabelian subgroup of my free group.
Oh, non-abelian.
Because W1 and W2 don't commute. That's where I'm using that. Okay. So the point is that this is generic. Okay. It's not open anymore, but it happens by Borel. This is a dense. This happens for a dense subset. And okay.
So what's the statement? So you have a set of AB such that he wrote some things, and then you finish.
So if I look at the pairs in S and S, so these guys are maximal tori. All 3 of them are maximal tori.
What does that mean? All 3 guys are maximal tori.
So the Zariski closure of the subgroup generated by these cyclic subgroups generated by these 3 words, when I plug in AB, is a maximal torus for each one of the 3 ones. Each one it's fine, and then I'm just throwing the conditions together.
So, and then what's the statement about that set?
So that this is generic, meaning in particular it's dense.
Oh, I see. You're fixing the set of AB such that that is a maximal torus is generic.
Right. So, for example, if you're over an
You're fixing AB when you write that expression there. You wanted to.
No, I want to look at the set. Yeah, I'm taking the set of AB that have this property.
You want to be kind of generic in the torus.
Correct.
The eigenvalues are generic. Okay.
Right.
Okay.
And now, what does that tell you about the subgroup generated by W1 and W2? It tells you, first of all, it contains a maximal torus. It tells you it's connected because this is in a maximal torus, it's in the connected component. This is in, this one is, and so the group generated by it is in the connected component of the group. So it's connected. It's also telling you that the commutator subgroup has maximal rank as well, contains a maximal torus, because there's this one commutator. Closure still on the commutator. So it's telling you, so this implies, this condition implies that the group generated by W1AB containing 2AB is semisimple of maximal rank. Of rank equal to the rank of S. So for example, if I'm in SLNC, it's telling you it's generating a semisimple group of rank n minus 1, which is the rank of SLN. Now, SLN, we're done. There are no semisimple subgroups of rank n minus 1 other than SLN minus 1. I mean, so for example, SL3 has rank 2. The only proper semisimple subgroups are all isomorphic to SL2 have rank 1. So for SLN, we're done. What we've shown is that the set of AB that generate the Zariski closure for W1 and W2 is SLN minus 1 is generic. Now this doesn't work.
Okay, so what does this prove now?
I've just proved for SLN, for example, that if I look at the set of pairs, so that this, and I fix a pair of non-trivial words not being in the free group, then the set of pairs for which this subgroup, the Zariski closure, is SLN, that's a generic set, meaning it's the, if we're over an unaccountable field, it's the complement.
Is that symbol there, that's the commutator?
No, it's just the subgroup generated by those two elements.
Oh.
Just the subgroup generated by those two things. Okay. Now it turns out, so in this case SLN is true. But now, for example, think of E8, for example. Well, the problem, what this tells you, there are some simple groups. In fact, that's why I said Burrell's theorem was actually trivial for E8, because it's just inductive. But unfortunately, it means that you have to work here. So in E8, for example, there are subgroups SL9. There is an orthogonal over dimension 16, which is rank 5. And in fact, there's about 8 or 9 maximal subgroups of rank 8 in E8. And so the problem is, you might not be Zariski dense in E8. You might conceivably be generating an SL9. But so what you have to do is show that, well, there's only finitely many possibilities up to conjugacy. So if I failed, I would have to almost always hit one of them. But the point is you play, but on the other hand, you know you can hit every single one of them by induction, and you show that you can't have one of them being a deformation of all there can't be one in which all of them are sort of deformations. I'm not going to define exactly what I mean by that. So for example, in the A, what you do is you play off, there's an orthogonal group of order of degree 16, and there's also an E7A1, an SL2 E7 in there. And you show that there's no other, you know you can hit those very often, and what you show is that those can't be deformations of any other maximal rank subgroup. And so there couldn't have been one that you hit almost all the time. It's the same reason that the irreducible subgroup, if it's a finite union of closed subgroup, is it must be one of them. It's that sort of thing.
In your field, do you feel the moral obligation to, when you state and prove a theorem that is a nice functorial statement, like proving things are strongly dense, that if you have a proof that uses the classification of Lie groups, that you should find an intrinsic proof that just uses the definition of Lie group?
Do I think it's
moral
do I think moral? I mean,
not moral,
moral.
What I mean, yeah.
But no, sort of, it would be nice to if you can understand it without doing that. But in fact, we do need in each case to know what the maximal rank subgroups are. And so we have to, and in fact, there is exactly one case where this argument fails. Namely, SP4 and characteristic 3. It turns out there's essentially only one semisimple group of maximal rank there. There's an A1, SL2, SL2, and characteristic 3, and there's no other semisimple groups that you can play off against it. And so this argument just fails. So we had to come up with a different argument.
It's still true.
It's still true, but by a different argument.
The theorem you stated, though, was characteristic 0 or finite characteristic?
Any characteristic. The theorem is any characteristic. Now let me just point out, since I'm running short, let me just now mention some of the applications. very quickly and that stuff. So here's an interesting one that sort of seems. So let's let S be, well, I don't want to say group scheme, but so let S be SLNQ, for example. So N fixed, I'm going to think of N fixed and I'm going to let Q vary. Then if I look at, and I take a W, a non-trivial, if I take W1 and W2 in the free group that do not commute, then the set of pairs, A, B, and S, such that W1 and W2 equals S now, or the size of S divided by the size of SLNQ squared tends to 1 as Q goes to infinity.
Is there a closure there?
What?
Do you have a closure there?
No, here I'm over a finite field.
Oh, I see.
So that we're talking about finite groups. So what this is telling you is that for almost all pairs, if I take any two fixed non-two, so I'm fixing the words now. So in particular, it says that A and B tend to generate. By taking W1 to be X and W2 to be Y, for example. But it says any two words. The probability that if I take a random pair that those two words generate the simple group, it goes to 1 as Q goes to infinity. I'm fixing N. And this goes by going to the algebraic closure, and then I basically have something like an open subvariety. It's not quite true, as I said, in positive characteristics. We have to be a little careful. And then using Langmuir, which tells you that open subvarieties are big.
Wait, so you have all this infinite family of finite simple groups, like SLNQ.
Right, but I'm fixing N.
And you're fixing words, and you have fixed two elements where where are you fixing these?
I'm saying the set of pairs that have this property is big. Most pairs, random pairs have this property.
Not only random pairs, but fixed words and random pairs generate.
Yeah, fixed words. Right, so less than, not just the pairs. Right. Here's the second one. In fact, even sort of a stronger property. It says if I look at the set of pairs S cross S in the same S, such that the Cayley graph given by the generators A, B is an epsilon expander. So now fix an epsilon. Here is a family of epsilon expanders. Okay, I don't have much time to explain this, but the idea is, what does a family of expander graphs means that if you have a subset of vertices, the boundary of that set is big compared to the size of the subgroup. So if you take anything at most half the number of vertices, then the boundary is going to be at least epsilon times the size of the vertex set. And this is big. The set of pairs with this property is big, and precisely in the sense that the probability that it's an epsilon expander goes to 1 as Q goes to infinity with N fixed. So exactly the same. And this was the original motivation why Terry and Ben and Madeline were interested in it, to prove this thing. So it's known that that there are pairs that exist. This says pick one and pick a pair that's almost certainly going to work. And the third application is to the Banach-Tarski. Really, I guess should put in Hausdorff problem, which is breaking up so originally for spheres, you take Sn, and at least 2, you want to break it up into 4 parts so that you can find translates of, you can find, also break it up into 2, so just very quickly. So you have your sphere, Sn, and at least 2. Can you write it as union of 4 subsets so that it's also equal to A union AB. And it's also, I might be screwing this up a little bit. C union. So you can write it as a union of these 4 subsets, but also as 2 of them, as long as you're willing to take translates, where A and D are in SO and plus 1.
SO.
Right. So this was proved by, so for an even, it was proved by Dennis and Deligne. For an odd, rather, and at least 3. For an even, Decker had a proof except for n equals 4. And then Burrell, using his dominance map, showed you could get it for all n. And the idea is, what you really want to show, it's known that it's enough to find an action of the orthogonal group. So you can find a free subgroup of the orthogonal group that had the property that, when n is even, it actually, the idea is that the free subgroup doesn't intersect the stabilizer of a non-degenerate point. When n is odd, what you want is that the stabilizer of a point is commutative. So you want to find a free subgroup. And Burrell did that by using the dominance map. What we do for our result is we can actually do it for any homogeneous space. Say let's take a compact Lie group. And you take any homogeneous space for that compact Lie group. You can find, and in fact, almost any pair, generic pair, will give you an action on that homogeneous space so that the stabilizer of a point in that homogeneous space for our subgroup is always available, cyclic, because it's a free group. And that tells you that any homogeneous space has this property. You can break it up into 4 subsets so that you can also get it as unit translates. And not only can you do that for any homogeneous space, but you can sort of, as long as you fix the big compact group, you can do all of them at once. You can find one free subgroup that works for all. And has the property of being strongly dense as well. And in fact, yeah, so, well, in fact, you need that because you want to avoid. You want to avoid, in particular, subgroups of smaller rank, you won't get by combining a result with Burrell. And the maximal rank ones you'll hit sort of just with cyclic subgroups. So I think I went over a little bit, so let me stop.
Thank you.
I should know better when Dennis is in the audience. You're going to go over. I know that. So.
Any questions?
No, it's a rule, but I enjoy it actually. It's nice to know somebody's paying attention.
I have a question. So all the statements were for pairs of elements A, B. Does it make sense to consider generalization?
Once we've done it for pairs,
consider any number of elements.
Any number. It's the same proof. I mean, once you know it for pair, you know it for just by general nonsense.
Is it worth saying what the background for asking is?
You would know better. You would know better.
Not speaker, though.
No. I mean, so I guess Hausdorff. Yeah. Well, I guess the idea is, you have a set, and can you break it up so that you've got pieces that you've got 4 pieces for it that it's a union of these things. But you can also sort of take translates, and you think, well, how the hell can you have translates of these subsets which also give you the set? Well, I mean, obviously they can't be measurable, but so it's sort of anti-intuitive. But on the other hand, once you interpret what you're asking, it's actually not so anti-intuitive. So I mean, these are sets are called 4 paradoxical, but there's really no paradox. So.
Well, okay, I will say that.
Okay,
You didn't answer it. Well, when you have something like that, you can't find even a finitely additive rotation invariant measure to find out all subsets. Okay. Because the measure of A, B, and C wouldn't add up right. It would rotation invariant. Right. Because you have covering 1/4 with 3.
Right. Yeah.
And it's still not known apparently whether you can have a non-trivial finitely additive rotation invariant measure on higher spheres, which is defined on all Borel sets, which is different from different from the standard one.
Right.
So that's still not known.
Oh. Okay. Oh, that's interesting.
So, and how the space of free groups look in the classical topology for SL and C?
Well, I mean, so it says that most things are free in a certain sense, so I'm not sure.
For the classical topology, for instance.
Oh,
so
no, so it's also true. I mean, most, you know, whose closure, I mean, well, so, I mean, most things are free, so it doesn't matter. In Euclidean topology, the results are
For instance, what would be the interior in the classical topology of this space? Would it be
Oh.
some kind of Schottky space or something?
that I don't know. That's a nice question, but I
What's the question?
What is, so if you look at the set of pairs that do generate a free subgroup, what does it look like sort of in the standard topology? What's the interior of that set? Does it have an interior? I mean, so,
For SL and for
I mean, it does have
SL2C is
interior.
probably
It
just
certainly has
a Schottky
interior.
space. For SL2.
yeah, no, I don't know. That's a nice question, but I've never, as I said, I think of characteristic P, so. But no, yeah, that's an interesting question. I don't know if people have looked at that.
Did you say it was risky dense?
Well, yes, certainly. The set of pairs.
The dense set is open and dense with classical topology.
Yes, right. So it's going to be very large, but yeah, but I don't know if there's more you can say. Right, it will be large. Yeah, it'll be dense, as you say. In fact, I mean, you know, it's missing all the measures of a subset, so it's huge. But I don't know if there's any interesting topology.
But probably there is some component of interior and then there is some dark region where this groups.
What?
Probably there is some open component of this space and then there is some big complement where the groups are dense and sort of regions or something like that.
I can't process the question. I heard that answer yesterday.
So it is for the classical Guralnick groups it should be known. I guess it is just the Schottky space probably is the interior.
What?
So for the classical Guralnick groups,
Yeah.
I guess just the Schottky space should be the interior of this
Should be
space.
what?
Should be the interior.
Oh.
Interior. Classical interior.
Yeah, I mean, at least for SL2,
What's
you should
it?
be able to describe it. I mean, because there it's either free or it's essentially contained in a Burrell or a normalizer or a torus. I mean, not quite true, but close enough. So there it should be describable.
We lost the chair.
You lost it. Chris, you told me how to
I have an announcement, so maybe I'll do the honors. Are there any other questions? If not, then let's thank the speaker again.